Hi there. In this video we're going to talk about absolute constants and hyperbolic trigonometry. We're going to talk about the isomorphism of the Cayley, Klein, and Poincaré disk models, the isomorphism of the two Poincaré models, the hyperbolic trigonometric functions, and what are called the absolute constants. Let's get started. So, we have these two disk-based models of the hyperbolic plane. We have the Cayley model and the Poincaré model. So, notice that in the Poincaré model, our lines are circles orthogonal to the boundary. So in Poincaré, we have one structure that corresponds to lines, and in the Cayley model, we have another structure that corresponds to lines. Now, there are certain things that make these two models sort of similar. One example being that we have infinitely many lines through P not intersecting AB. And in the other model, we have infinitely many lines through P not intersecting AB. And what's really remarkable is that these actually model the same mathematical structure. The Cayley model is also the hyperbolic plane, just like the Poincaré model. So, how are these things related? We've got an app in GeoGebra that'll model the isomorphism between them, but briefly I want to show you what's going on with this picture. So the chord xy, from here to here, this is the straight line that passes through the point A. So this chord corresponds to a geodesic xa prime y that passes through A prime. So this straight line xy corresponds exactly to the circle xa prime y. So objects in the Cayley-Klein model map on one-to-one bijectively and continuously onto objects in the Poincaré model. Okay, so I encourage you to check out the GeoGebra app, play around with it, and get a feel for what this isomorphism is doing. Now, we have two models due to Poincaré. We have the Poincaré disk and the half plane. So the disk is d squared, and the half plane is c plus. So the definition of d squared is all of those xy such that x squared plus y squared is less than 1. And there's a very beautiful map, a fractional linear transformation that takes this onto the upper half plane in the following way. So this map, omega, maps these points correspondingly. You can calculate out that, for example, 0, when we plug this in, must get sent to I. So if we calculate f of 0 is going to be I times 1 plus 0, 1 minus 0, which will be I times 1, so it will be I. So we see that this 0 is going to get sent to the point I. Now, I encourage you to do a couple more of these calculations to get a feel for what's going on. But the idea is that the entire disk is mapped, stretched out, and put onto the upper half plane. This induces an isomorphism of geometries, that H2 with the group of transformations is isomorphic as a geometry to the upper half plane with the real Mobius transformations. So what do we have? We have this incredibly beautiful theorem to end our course with. The three models of hyperbolic geometry. This disk with circles orthogonal to the boundary, this half plane with circles orthogonal to the boundary and vertical lines, and this disk with straight line segments. All three of these models model the same reality, the same hyperbolic plane, in different ways. Now let's talk a little bit about hyperbolic trigonometry. The hyperbolic trigonometric functions are defined by the following relations. So hyperbolic sine is e to the t minus e to the negative t divided by 2. Hyperbolic cos is e to the t plus e to the negative t over 2. Okay, so these are exponential functions. And we have the following theorem that is very similar to a Euclidean theorem about angles. So for a hyperbolic triangle ABC with sides ABC and angles alpha, beta, gamma, we have that hyperbolic sine of A divided by sine alpha is hyperbolic sine of B divided by sine beta is hyperbolic sine of C divided by sine gamma. So this is a sort of hyperbolic analog of the sine law for Euclidean triangles. And what this allows us to do is it allows us to calculate lengths in hyperbolic space. Now, there's a subtle difference between lengths in hyperbolic space and lengths in the Euclidean plane. And that's the existence of what we're going to call absolute constants. So in the Euclidean space, there is no natural unit of measurement. There's no natural way to assign lengths to objects because similarity of figures implies there's no natural reference point. So let's look at these two triangles, for example. If we call this length 1 unit, then this length here will become, say, a half unit. But we could just as equally call this guy, this red line, our special defining unit. We could call this 1 length. And then this winds up being 2 lengths. Right? Because of the notion of similarity in Euclidean space, we can't say that the blue line is the defining unit of length or the red line is the defining unit of length. Each one, the red line or the blue line, could serve as a basis for our geometry. And we could do the exact same thing with areas. We could call this 1 area. And then this would be 1/4 area. Or we could play the game in reverse. There's no natural place to start when you're in the Euclidean plane. However, in hyperbolic geometry, there are natural choices of units, which is very, very surprising. So, a natural choice for the unit of area is what we call the ideal triangle. We know that the area of a hyperbolic triangle satisfies area is pi minus alpha minus beta minus gamma, and that tells us that as long as alpha, beta, gamma are positive, the area is going to be less than pi. And the largest triangle, therefore, in hyperbolic space has area exactly equal to pi. And we can make it in the following way. If we pick our angles to be alpha equals 0, beta equals 0, and gamma equals 0, we wind up with the following triangle. We wind up with a triangle that has all of its vertices on the absolute and has total area in here having area equal to pi. So this ideal triangle creates a notion of area for us. It defines the natural unit of area on the whole hyperbolic plane. So this is our reference triangle. There's also a natural notion of length called the Schweichart radius. So given a pair of perpendiculars OA and OB, they're going to meet the absolute at 2 points x and y. There is a unique line passing through both x and y. The distance from the origin to that point is the Schweichart radius, which we call sigma. So what do we do here? We start at the origin, we make a ray OX, we make a ray OY. Now, those are going to meet the absolutes at points x and y. Now, we can form a unique hyperbolic line passing through both of those points. Right, this is the arc xy. And the distance from the origin to that xy is a unit of length that depends only on the structure of the hyperbolic plane. This gives us a natural notion of length, which we call sigma. So there's very special quantities in hyperbolic geometry, the area of the ideal triangle and the natural unit of length, sigma, which are completely different than what we'd expect from our Euclidean experience. Moreover, there's no notion of scaling or similarity in hyperbolic space, which means that we don't have this paradox about the red line and the blue line. So thank you for listening. We'll take up more of these ideas in class.